commutators. Derive some conclusions from commutators. And the third one is the concept we call the superposition. That's the last section in chapter 4, and also you will see that actually superposition is represented by the Fourier transform. And we'll talk about that. Okay. So the first one about formal postulates. So formal postulates are the quantum, as the basis for the quantum mechanics, or quantum mechanics we learned in this class is actually built on those postulates. Okay. So a quick review of last week. We have went over postulate number 1, and from number 1 we divided 4 layers of meanings. Okay. We talk about statistical meaning of wave function, talk about normalization, and how we can calculate the probability and the requirement for a well-behaved function, or well-behaved wave function. So those are all included in postulate number 1. So actually it's a pretty huge topic there. Okay, this is what I went over from last time. So this time we're going to go from number 2 to number 4, and we don't care about number 5. Time-dependent Schrodinger equation is pretty important for the applications in spectroscopy. But in our class, we will not talk about time-dependent. We only care about time-independent things. This does not mean this one is not important, but simply because of the requirement of our class, we will get rid of this part. So forget about number 5. So let's go back to number 2. So number 2 talks about classical observables and quantum operators. So it simply talks about correspondence, okay, between two things. The first thing is the classical observables corresponds to the quantum operators. Okay. For those classical observables, that's something you learn in physics. Like the location, linear momentum, angular momentum, trivial energy, whatever, total energy. All those physical properties of a system. And they are corresponding to a certain quantum operators. And the operators are always linear and Hermitian operators. Okay, we'll already talk about the linear operators, but later we'll talk about what is a Hermitian operator. Okay, but anyway, so here postulate number 2 talks about any location can correspond to one quantum operator, which is linear and Hermitian, and which we can refer to table 4.1 that shows you exactly those observables you can get correspond to the operators, so all those operators. Okay. So if you want to observe the kinetic energy, you just use the kinetic energy operator to operate on the wave function that will give you back the kinetic energy. So something like that. Okay. But here number 2 just talks about correspondence. So just let you know there's a relationship between the two things. Okay. Okay, so let's talk about a Hermitian operator. So I want you to be clear about the definition. Okay, what is a Hermitian operator? If we ask you to prove, you simply need to show us this definition. It satisfies this definition, then it is a Hermitian operator. Okay, so it talks about an integral, okay, related to a complex conjugate. Insert the operator in. So this A operator, let's say we want to tell if it is a Hermitian operator, we just simply need to insert the operator in between two wave functions. Okay, one is a complex conjugate, another one is the wave function itself. So if the left-hand side equals right-hand side, so simply see you can change the start. So it's simply you start the whole thing. Okay, how you memorize it? You just start the whole thing. So the complex conjugate after starting is also return to the wave function itself. And operator is star, you get star, and wave function itself, star, you get star. Okay, so you simply change the star positions. And it talks about m equals n or n does not equal to n. So this two functions can be the same function or can be the different functions. Okay, if they satisfy that, it is called an Hermitian operator. But anyway, based on postulate number 2, we know any classical observables, they correspond to our Hermitian operator. So any like kinetic energy, the literal energy, total energy, they correspond to some operators which are Hermitian operators. Okay? And the characteristics of Hermitian operators, First one is eigenvalues must be real. Okay, the eigenvalues actually is the classical observables. Like what we mentioned before, location, momentum, whatever. It must be a real number. Okay. So, for example, we have the eigenfunction, eigenvalue program like that. If we know A is a Hermitian operator, and we give you the eigenfunction A here, and A equals A star simply because A is real. Okay, any question about this notation? Okay. The second one is different eigenfunctions of the same Hermitian operator must be orthogonal. Okay, different eigenfunctions of the same Hermitian operator must be orthogonal. And do you still remember how we can prove orthogonal or not? Similar expression as normalization. Okay, similar. But this different thing is the subscript will be different. So one is m and another is n. So in this case, m is not equal to n. So if m and n are not the same, and you prove that they equals to 0, they equal 0, then simply means the two wave functions, the two different wave functions are orthogonal. But if m equals n, that means if you do the same wave function, then you prove if that equals 1, then you prove normalization. So in this case, I want you to be clear that normalization and orthogonal, they're actually different things. Okay. So based on this, we developed another concept called orthonormal. And the definition for orthonormal is pretty simple. Based on the word, it's normalization plus orthogonal. Or normalized plus orthogonal will give you orthonormal. So actually 2 layers means there. Okay. So then that we introduce another concept called the Kronecker delta to actually exactly represent the meaning of orthonormal. So by doing this. Okay. If I just give you the expression like that, and I just did not tell you what's the relationship between n and m, whether they are equal or not, the only value you can get is just a Kronecker delta here. And Kronecker delta with the two subscript n and m is actually the same n and m here. And this notation here is actually represent 2 things. The first one is it equals 1. It equals 1 if m equals n. So think about that. If m equals n, actually the 2 wave functions are the same, right? So this expression represents what? Normalization. That's how you do normalization, right? Except you have an a squared when you try to calculate that. But anyway, this part, the main part is actually related to normalization. So if it equals 1, simply means to this one wave function, it is normalized. Okay, this is the first layer. So for the same wave function, we talk about normalization or not. Okay, and then we'll emphasize that. So the second layer is n equals 0 if m is not equal to n. So looking back here, m is not equal to n simply means there are 2 different wave functions. So that's I don't have access to GroupNet. Okay. So different wave functions we talk about orthogonal. Or not orthogonal. So orthogonal plus normalization we talk about orthogonal. So you will see some questions asked you to prove, give you maybe 3 wave functions or 2 wave functions and ask you to prove they are orthogonal. So when you see that question, just keep in mind you need to do 2 things. Okay? To prove orthonormal, the first thing is you need to prove normal. They are normalized. Okay? Each of them are normalized. And another thing is to prove they are orthogonal. They are orthogonal is simply you use 2 different wave functions and do the integral. Okay? So I give you 2 wave functions actually to ask you to prove orthonormal. How many integrals do you need to evaluate?
2.
Just 2? So for 1, so what are the 2? The answer is 2. What are the 2?
Can you repeat what you were asking?
So if we have a question asked you to prove the 2 wave functions, they are orthonormal, how many integrals or how many integrations do you need to evaluate? You need to show. 3? What are the 3? normalize.
Like normalizing each one of those.
Okay,
and
great.
Checking, and then after you normalize both of them, then
You check the
put
two.
them in that one.
You do this one, right? So there are three integrals in U shell. The first two, they are related to normalization. So you simply plug in, they're still the same expression here, but you plug in the same wave function. That's two. Okay, there's two to prove normalization. And then another orthogonal is to repeat the two. Okay, it doesn't matter one or two here. Okay, one here, two here, or two here, one here. It doesn't matter, they're the same. Okay, so then you only do one. So 2 plus 1, you do 3 evaluations. Okay, so just keep in mind. Okay, so now we'll go to postulate number 3 about observables eigenvalue. Okay, this is pretty straightforward. So then it talks about a microstate which is composed of a single eigenfunction set here. So for one, all those are for the one operator. So for one operator, we have a set of eigenfunctions. So for each eigenfunction, if we operate on those wave functions, we get corresponding eigenvalues, and we have eigenvalue set. And your textbook is called this set is called the spectrum of the operator. Okay, so simply means we have two sets. We have eigenfunctions, we have eigenvalues for a given operator. So postulate number 3 talks about the measurement. So for each time you can measure. Let's say we have the location operator to operate on the wave function. So it will give you back the operation, the location, right, based on number 2. And based on number 3, it tells you can only get one of them. Okay, although you have a set of locations here, but only get one. So let's say measurement 1, you measure this state, and this will give you this eigenvalue. And measurement number 2 will give you this state, and then you get this eigenvalue. Okay, so simply means there are a set of things, eigenvalue you can get, but for each measurement, you only pick one. So from here, we can derive probability, which directly leads to superposition we'll talk later. Okay, and everything is a straightforward postulate. Any questions about this? Postulate number 4 talks about expectation value, or in our lecture, we say average value. They are the same. Okay? Again, to do anything related to the integral, including the expectation value or average value, please check normalization first. Okay, please check normalization first. Unless the question explicitly tell you we have normalized wave function as follows. Otherwise, always remind yourself before doing any evaluation later I show, check the normalization. Okay, let's say you check the normalization and you got the normalized coefficient and you successfully normalize the function. Then you can do the thing. The expectation value or average value is expressed as this. So the same thing, you have the same wave function, complex conjugate and itself, but the only different thing compared to normalization is you insert the operator which corresponds to this observable here in between them. Okay, then by doing so, I want you to remind you is this operator operates on this wave function, they become one identity. Simply means you cannot switch the position between the two. Okay, they fix. It's not like normalization. Normalization you can switch it, but for expectation value they are fixed. The position are always there. So when you do the evaluation, make sure you do this first, right? It's operate on that first, and then you do the whole integral. Okay, I'll give you the average value, and of course the bounds are within the whole space. Okay, within the whole space. It's not like probability. Probability is within a certain space in the whole space. Okay. Based on that, once you get average value, you can calculate the variance. Variance is defined as two average values, but with different combinations. So the first one is a square average value minus the a average value per square. So after the two, they're different. Okay, they're different. So once you get variance, you can calculate standard deviation. Simply you take the positive square root of the sigma a squared, and you get this. And that's called standard deviation. Okay. In this part, we can just ask you to evaluate this one and give you the equation here. So simply you just need to know how can you evaluate that and how can you evaluate that. Right? For this one, you get this e squared, and that's this term. But for a squared, you simply need to insert the a operator squared. Okay. Any questions about this? Okay. If not, then we talk about operators number part 2, which addresses the commutator. Okay. For the commutator, again, the definition is we can use this notation with a bracket to include the two operators, and it equals AB minus BA. Okay. So based on this definition, I want you to tell you what's the relationship between these two commutator. That one equals what? Equal?
No.
Equal. Then what's the relationship?
You switch.
It's
On the
switching.
right and on the left.
So there should be what?
BA minus AB.
BA minus BA, this is AB minus BA, so the relationship between the two with only one what? Right, negative sign. Okay. Gotcha? Gotcha? AB minus BA. This one is BA minus AB. Gotcha? Okay, so this one tells you when you write a commutator, the sequence, which one is first, which one is second, is actually matters. Okay, if you switch them, you have to change the sign of the commutator. Okay, so this is the definition. And the operators, we know, they do not always commute. Right? They do not always commute. So if you plug in this, AB is not always BA. So AB, this commutator, do not always be 0. And not always 0, but sometimes yes. So if two operators commute, then we know a commutator equals 0. So this is a really important conclusion. If two operators they commute, their commutator must be 0. Okay. And based on the commute, if the two operators commute or their commutator equals 0, we can derive two very important conclusions based on that. So the first one is the corresponding observables that can be accurately determined simultaneously. Okay. Or in other words, uncertainty principle does not apply to those two variables there. Okay, let's say the A is, let's just make up something. A is location, B is whatever, energy or whatever, momentum. So if the two they equal 0, okay, the commutator equals 0, that means the location and the momentum can be simultaneously determined. This is simply because the uncertainty involves the commutator inside, and if the commutator equals 0, the actual uncertainty, the minimum uncertainty can be 0. So we can reach 0, simply means we can accurately determine the two things. Okay? So can you tell me without calculation, what is this commutator? What does this equal to? Just tell me the sign, so compared to 0. Okay, two things. Is equal or not equal to?
Not equal?
Not equal why?
Because they don't commute.
They don't what?
They don't commute.
They don't, why they don't commute? Do you still remember Heisenberg or uncertainty talks about what? Can we simultaneously determine the location and linear momentum? No. So no means the two, if they commute, then they satisfy this, and then they violate uncertainty principle. Okay, because uncertainty principle tells you that we cannot simultaneously determine the location and the linear momentum of the particle. And those things here, location, linear momentum, they are the classical observables corresponding to the operator here. So this too, we cannot simultaneously determine the accurate number, so the commutator must not be 0. Okay, must not be 0. It should be a non-zero value. Okay, understand that? Okay. You don't need to evaluate that. It's actually based on what you learned in chapter 1. You can directly tell. Okay. This is the first conclusion, is whether the uncertainty principles is valid or not here. The second one is the two operators, they have the mutual set of eigenfunctions. So simply means they share the same set of eigenfunctions. Okay. So my question is, we know those are really important. We can derive two very important conclusions, but how to tell if two operators commute? Like one thing is based on what we learned before, but let's say we change to another operator and we don't know. So how can we tell if they are commutable? And when we introduce that, right, simply show us commutator equals 0. Commutator of the two operators equals 0. But another question is how to tell commutator equals 0. So then that will lead you to the evaluation of commutator. Okay, simply 4 steps, and you can tell. First step, so this is our question. There might be some questions in your homework and also in the exam to ask you to evaluate this commutator. Okay, pretty common questions. The first step is please introduce an arbitrary function f. Here in the arbitrary, you do not need to specify what the function is. It's just f. It's something like when you prove linear operator, you get the combination c1 f1 plus c2 f2. Those f1, f2, they are just arbitrary functions. We don't even care what are they. Okay. So you introduce an arbitrary function behind the commutator. Okay, and then the second step is expand the commutator using definition. So we know AB here means AB minus BA, right? They operate on F and mass. You write it out. So this is a general expression for any specific question. You will get a specific form of A and B. So then you just simply plug in. The third one is plug in two operators and evaluate. And you get another operator operate on the same arbitrary function F. Well, that depends on your math, I know. Okay. So you should be able to get a common operator operate on a certain function. So something like the eigenfunction eigenvalue program. And the fourth step is take off F, and then AB equals C. So the commutator is the operator C here. Okay? 4 steps. So let me give you one example so you can better appreciate the ideas here. So you can read the question. We'll give you two operators, X and B. Can you tell me what's the name of the A operator? What operator A is? Well, location operator. Okay. What is B? Linear momentum operator. Okay. So tell if the two operators commute or not. Of course, they do not commute because of uncertainty principle. But how can we show? Okay, let's say we want to evaluate that. So show us what is this. I should give you an operator. One example. So the first step is like you still remember when we do the evaluation. If they to 0, then you just assume they commute. I mean, when we do the evaluation, we want to say whether it's 0 or not. The first step is what? Go back. Introduce the arbitrary function F. Okay. And the second step is what? Expand it using definition. All right.
Did we establish if they did commute or not already? Did I miss that?
Which one is established?
Tell if the two operators commute or not. Did we answer that already, or
Or you want to say
are
that
we
you don't
trying to
have
find that right now? Or?
You want to find it right now.
Okay.
You want to find it. Okay, this is second step, right? Third step, what? Finding operator and do the evaluation, right? So what's the x operator here? This equals what? Just x. I multiply x. And px actually show you here. So it's I h bar d over dx. df over dx. That's first term. Right? Second term is minus I h bar d over dx. And here is x operate on f by x, just multiply x. Do that. Okay. So let's use our math to do it. So this is not quite interesting. Just I h bar x df dx. So we don't know what the f is, so we cannot evaluate the derivative here, so let's keep it. So here there's something interesting. We're taking derivative with respect to a product here. Right, so something like you already math, we have UV, and we're taking derivatives. And we need to use what to evaluate? Or what rule? A chain rule. So that's why we use U times V plus V times V. Right? Same thing here. The X is U, Fx is V. Okay, let's use chain rule and with clocking, and you will get. So the first one is, so U is X, so will be dx, dx times F plus X times df. Okay? Okay, dx over dx is what?
1.
It's 1. Then equals what? This term cancel with this one. Right, this one minus I h bar, this one. They're the same. Right? Great. Well, you go back to regular math anyway. So, can you tell me what is the operator? Or what is the commutator? The fourth step is what? Take of f. With negative f. So of course, from here you know, it's not equal to 0. It's not equal to 0, then the first question is tell if the two are commute or not. Yeah. Okay. Second one, if not, what is the commutator here? Negative IH1. Okay. Third question, can the two operators have the same set of eigenfunctions? Can they? Can they? They cannot, right? Only if they commute, they have the same. If not, they don't have. Okay. That's one. But by the way, if this is the really small questions, actually you don't need to show the evaluation because you already know these two operators, they don't commute because of the uncertainty principle. So location and linear momentum cannot be simultaneously defined or better, so they're not commuting. Okay? Are there any questions? Any questions? You must know how to evaluate a commutator. Okay, must know questions. So next part, we'll talk about superposition. So introduction about superposition. Is this the first time you heard the word superposition? Is it the first time? So it's the first time when you go a little bit slower. Okay, so all the things come from Schrodinger equation. Time independent Schrodinger equation. So we'll see there's the wave function here and also the wave function here. So it's pretty easy to prove. It's pretty easy to prove that if the psi, this one, is acceptable in this in this equation, or simply means this is one solution for this equation, for the Schrodinger equation, then we can times the coefficient c in the front of the wave function. And we can also prove that this c times wave function is also another solution for this Schrodinger equation. Okay, so we can easily prove that. And we get one more. We can combine a lot of these terms together, a lot of c times wave function together with different n values, and we sum them all. And we can also prove that this summation is also the solution of the Schrodinger equation. Okay, so based on that, simply it indicates that for a given microstate here, the wave function here, it can be this. It can be something with the coefficient, or it can be a linear combination of all the c times psi here. Or if you go think back about Schrodinger equation, the meaning of Schrodinger equation of the wave function is the wave function actually can talk about a microstate. So this one can represent one microstate. This one can also represent the microstate. So for this one. Okay, so here are all the accepted. By a linear combination of several wave functions, it can also describe a microstate. So then we go one more. So this expression actually just means superposition. Okay, for a given microstate, the wave function can be expressed by the sum of basis wave function into the small letter side here with the corresponding Fourier coefficient. So all those c here. Okay. So let's take a look. So left-hand side here, this capital letter psi means the wave function of a microstate, or simply means the total wave function. So it's all the wave function is a whole. The wave function of a microstate, and all those CIs, they are Fourier coefficient. Okay, just some numbers. And those psi I, the small letter psi I here means the basis wave functions. So this is actually, so this part talks about superposition. And also, if you not quite similar with the summation psi, you can just expand it. It will give you like that. So why do we call this superposition? So here, maybe based on this expression, it's a little bit hard for you to understand. But later we'll give you two examples. But here I just want to tell you the mechanism is, for this microstate, actually, if you measure it, it's actually represented by the Fourier combine or transform of all those psi 1, psi 2, psi 3, psi n. So your particle within this microstate actually can be found either in this state, or in that state, or in this state, or in that state, with different probabilities. So it simply means the particle can be everywhere. Okay, one simple example is we put an electron into our classroom, and we define our classroom in the whole space. But every moment, every time moment, when we open the door, we check the location of the electrons. Actually, we can find everywhere, right? They can be here, they can be there, they can be here. And we define each location has another basis wave function, and all those wave functions combined together give us the wave function of the whole classroom. And within that picture, means we find the electrons with the different locations within the classroom. Okay, so here's just a picture about superposition. So superposition means you have several positions superposed together. It's something like everywhere. It's like a ghost. Okay. And for each Fourier coefficient, you actually can use this equation to evaluate it. Okay. You do something like normalization, or something like normalization, but keep in mind, normalization you need to use the two same wave functions. But here we use, okay, the first one is the total wave function, but as complex conjugate, you can choose each basis wave function. So let's say if you want to get Ci, you just choose the basis wave function psi I. If you want to get C2, you just choose psi 2. Okay, you evaluate that, okay, and you can check the handout for proof why this is true. Alright, anyway, the conclusion is, if you can extract the coefficient out from the total wave function here, You simply can do this evaluation and it will give you the CI. Okay? One more thing about the basis wave functions. So what are they? So first thing, the requirement is they must be orthogonal. So here I mean orthogonal means the psi1 with psi1 itself, they must be normalized. But psi1 with psi2, psi3, psi4 to psi n, they must be orthogonal. Okay, same thing for psi2. Psi2 here itself, psi2 with psi2 must be normalized. But psi2 with psi1, psi3, psi4 until psi n, they must be orthogonal. Okay, this is the first requirement for them. They must be orthogonal. The second thing is they can be multidimensional. Okay, so each side here actually can be one-dimensional wave function, can be two, can be three. So let's say that there are particle in the box wave functions for you of them. The particle in the box, there's a wave function that can be one dimensional, can be two-dimensional, can be three-dimensional, depends on the dimensions of the box.
So this equation just accounts for all the possible wave functions
All the
in
in a given microstate.
a given. Okay. So this is like a particle in a box situation, but
But
with
with
every dimension together.
Every dimension. Okay, there's everywhere, it's superposition. Okay. So here, still remember that? For each wave function composed of different dimensions, the total wave function of that particle, of that system, is just by multiplying all the wave functions from different dimensions. So remember that in particle in a box, we know, right? When we talk about a three-dimensional box, we talk about the wave function. We simply need to know each dimension, what does the wave function look like? And then we times them together. So here I show this equation in here is I want you to be clarified, or to be clear that within basis wave function, you actually can times them together if the basis wave function is multidimensional. But for the total wave function here, you need to add them together. It's actually a summation. So multiplication and summation have different locations here. Okay, again, a little bit tricky. If we talk about the total wave function, about superposition, whatever, you combine each basis wave function by adding them together. But for each single or individual basis wave function, if we have multi-dimensions, then you just simply you find the wave function in each dimension and times them together. Okay? So this expression actually only applies for each one here and here. But you can actually add those things together and give you the total. Okay, that's the thing I want to remind you. So don't confuse. So someone say, oh, we talk about particle in a box. We say the wave function for different dimensions, they must be multiplied together in order to give you the total. But why here is adding together? Well, the multiplication only applies for each one. But when you talk about when you get out of the basis wave function, when you look over them, you add them together. There's some layers here, so don't confuse. Okay, then we can also normalize this total wave function as well. Okay. What I talked about before is those basis wave functions actually they are orthogonal, they are normalized. But we cannot guarantee that by linear combining them together we will also give a normalized wave function. It does not. No, sometimes it does not. So here we have the problem is how can we normalize the wave function? Where all the normalization is actually, the normalization coefficient is this. So to normalize this wave function, you simply need to figure out the coefficient in the front of each basis wave function. And that's the way to normalize it. And the normalized coefficient actually can be evaluated in this way. It's actually pretty straightforward. So let's say if you want to evaluate, you want to find the C1, the normalized coefficient for the basis wave function psi1 here, you just need to square it. Okay, I use the two vertical lines in case the coefficient sometimes will be a complex number. But we just need to square it, divide by, to square each coefficient together, and add them together. Okay, this looks like that. Take square roots to give this. So this is how you normalize it. Okay, this is a very important equation. Okay, very important. And if all coefficients are normalized, so let's say you successfully normalize it, you find all the CI norm. So then all the CI norms square it, you add them together, they must give you number 1. Okay, something like that. So if I have or something like that. So this is C1, this is C2, this is C3. Okay, and you can check C1 squared plus C2 squared plus C3 squared, they give you 1. So once they give you 1, we say this total wave function is normalized. Okay.
How do you know which of the constants to use in the top part, let's say?
That depends on the one you want to determine. So let's say if you want to determine the second one, what is the normalized coefficient, then you choose the second one.
And in the bottom part will
We'll
always
get all of them together. Yeah. So simply means if you have 3 basis wave function, once you normalize it, the total one, you can do 3 calculations. Each one without each function. Okay, questions? Any more questions about that part? Okay, so I will introduce to some very important conclusions. Okay, those things. And I will show you the derivation in the handout if you are interested. And another set of very important conclusions related to probability. Okay, probability of finding something. So the probability is, so when you talk about probability, the first thing to remember is to normalize the wave function. Okay, I mean normalize this wave function, okay, total wave function, by doing so. I showed before. And then the probability of finding the microstate here, finding this total wave function, this microstate, in the state described by a certain basis wave function psi I, is this one. Okay, actually pretty straightforward. Okay, so in this part, the linear combination part here, the superposition, the hard part is the conceptual part. The easy part is the evaluation part. It's the calculation. If you not memorize, if you know the equation, which one you want to use, you simply plug in, you get everything. Okay. So first one, you need to normalize. So you normalize the coefficient. And let's say if you want to find the probability of finding the state in the state I, the probability is just the square of the coefficient. So again, here I mean vertical square, vertical 2 lines represent. So sometimes we have a complex number here. You make sure. So CI equals A minus BI. So CI square, this square, not the bracket square, okay, equals A minus BI times A plus BI. That would be what? A squared plus B squared. Okay, something like that. Well, probability is the coefficient squared, vertical I squared. Okay. So let me give you one example. Okay. First example about superposition to help you understand. The question is, I give you a map of Upper Campus. The question is, where am I? Okay, where am I? So let's assume you don't know I'm doing a section here. Let's say there's a student from section B or section C. They don't know where am I now, but they can guess, right? They can guess, oh, maybe he's in Chris B College. Maybe he's in graduate student housing. Maybe it's in EE building, physical science building, the science and engineering library, health center, or in social science 1 here. We can just guess, right? They must be on campus. Okay, so for each one, so each location, let's imagine I'm an electron. Okay, I'm a small particle in a microscopic world. Each location is represented by a basis wave function to describe that location. And now I have this one. So if you don't know, if you don't catch me, you don't know where exactly I am, So the possibility of finding me in those 7 locations are actually, they are equal. Right? So if we assume we have equal probability everywhere, then the total wave function of my location, okay, the total wave function of my location is composed of the 7 basis wave function linear combination of all the together. So I have 1/7 chance to find me in Quest B, 1/7 chance to find me in graduate student housing, 1/7 in WE, so on and so forth. So this is actually exactly the picture of superposition. So think about it, I have like different parts everywhere. Everywhere with just some different or the same probabilities. So this exactly shows me the superposition. Okay? So this is the thing. So if equal probability everywhere. But if some places are ruled out, so let's say, because I'm a graduate student, so you cannot find me in Cresty College, which is an undergraduate college there. Okay, ruled out. And I have my own office, so I don't need to work in the library. So ruled out. And I'm quite healthy, I never go to a health center, so health center ruled out. So we have 3 positions ruled out. Then that corresponds to their probability of finding me there is actually 0. Okay, so therefore a coefficient now becomes 0. So simply means it's impossible to find me there. And in order to normalize the wave function here, those coefficients you must change. And once you change the coefficient, simply means the probability also changes. Right? It's pretty natural to think, because if you rule out some locations, so the probability of finding me in other locations, they increases. The increases, the reflect in the expression is the coefficient increases. Because we know the probability of finding me here is actually square of this coefficient. The probability of finding me here is the square root of that coefficient. Okay? Clear with that? Okay, let's say, but if with some preference, the preference, then you say, oh, you check the time, it must be the section time. So it's highly possible that we can find that person in this location. Okay, so this is the preferred location. So once you prefer that location, the probability of finding me in this location is actually also increases. So increases means the coefficient now is also increases. And in order to normalize the function, in order to finding me on the campus must be 1, so other coefficients they must be decreased. So simply means the probability of finding me in other places will decrease. Okay, make sense? Makes sense. Let's go one more step. If you catch me, you see me actually, I'm doing a section in Social Science 1. So I must be there, right? Those simply means other locations are all ruled out. Only one location. So in this case, my wave function here will be just 1. So now the coefficient will be 1. So the probability will be 1 simply means I must be there. And from that you see that actually the superposition now fixed to one position. They collapse. Or you can also think about that way. It simply means you measured my location. And once you measure my location, you get one eigenvalue out. That's based on postulate number 3. So you got the eigenvalue out, you actually see me, so my superposition disappears and only collapses to one state here. Okay, go to the picture. So already. Any questions? Any questions? So here I'll show you the example to show the relationship between probability, the real picture, and also the expression. Okay, by varying the coefficient, it actually changes the physical picture. Okay. Second example, relative to one of the 3 famous monsters in physics. Okay. You know the 3? First one, Schrodinger's cat, Maxwell's demon, and Popoff's ghost. But in this class, we'll only talk about the first one. Okay, in thermal, we'll talk about that one. But if you go to graduate student in graduate study in physics, we talk about field theory, we can talk about that, but that's more advanced. So for Schrodinger's cat, it talks about a thought experiment. So it's not a real experiment, it's just a thought experiment from Schrodinger. So Schrodinger thought that, well, we can see a cat in a box. in a box. I don't have a switch here, which is controlled by a radioactive element. And within 1 minute or within a certain time period, the probability for this radioactive element to decay is 50%. So we don't know whether it will decay or not, but just with 50% possibility that it will decay. Once it decays, it will trigger the switch here, and the hammer will smash the bottle, and will release all the toxic gas sealed in the bottle. So actually the cat will be killed. But within only 50% possibility, right? Because the decay is actually 50% possibility. So now we can see actually within the box, if we don't check the cat, we don't check the open the box. Most of the cat have two things. One is the cat is dead. Another one is the cat is still alive. Right? So I have two different situations. Okay, so let's take a closed loop cat. Before opening the box, we have 50%. We have two states here. Dead cat and alive cat, they have both 50% possibility. So simply means if we translate it to quantum language, it will talk about actually this. Okay. So this superposition composed for the cat, composed of a dead cat and a live cat. And the possibility of finding the cat in the two different basis wave functions, they're the same. Each one equals 1 over 2. So when you square root it, you get 1 over square root 2. So this tells you what? Tells you you can find a cat which is both dead and alive in the box. So here, I mean, if you don't open the box, the cat inside of the box actually is both dead and alive. Cannot be true. Horrible, right? It's like a ghost. How can a cat be both alive and dead? But actually, it's true, based on quantum mechanics. So we say the cat is now in a superposition composed of two states. One is the dead state, and another one is a live state. And the probability of finding the cat in each state is actually the same, which equals 1 over 2. Okay. So this is actually a Google Doodle, like one time, talking about Schrodinger's cat. Okay. So they use Dirac notation. Actually, I can say Google's engineering are pretty good at math. They use Dirac notation that equals the coefficient. So the coefficient, actually they normalize it, you see that? The no normalization, you normalize the wave function and get 1 over square 2 for the dead cat and the dead cat and the alive cat. So that's actually the day they memorize it, try to memorize Schrodinger, the birth state of Schrodinger. Okay. All right, functions? Okay, let's go one more step. If we open the box, so if we open the box, we can never find a cat which is both dead and alive, right? So in that case, either this is a dead cat or is a alive cat. So the superposition actually again collapsed to only one state with probability of 1. So you either be a dead cat or be an alive cat here. The total wave function of the cat must be this one or be that one, with probability equals 1. So here I want to say is measurements lead to the disappearance of superposition or probability, which in a formal language called the collapse of wave packets. So before we have superpositions, everywhere basis wave functions are off. But once we measure it, we only get 1 back. That's actually exactly possibility number 3 talks about. When you do the normalization, when you do the measurement, you always get 1 of the eigenvalues back. Okay. And based on this picture, is you get the 1 of the eigenvalues back, and at the same time the probability disappears. So the state collapses to the single eigenstate which gives you that eigenvalue. Okay, so that's a picture of the picture. Any question about this? That's the Schrodinger's cat. Actually, it's talking about a dead and a alive cat. Okay, but once you open the box, it will disappear. Okay. If no more, one more thing about this linear combination is, well, we know how to normalize them now. We know how to calculate the probability now. And the third one is we can actually evaluate the average value. So the average value of a certain classical observables can be calculated this way. So the only different thing is you change the psi 1 here, 2 is corresponding eigenvalue. Okay, to A1, A2, A3, whatever. Add them together and give you this. So again, I want to emphasize the calculation within this part is pretty straightforward. There are just 4 or 5 equations here. You pick the right one, you plug in the number, and you get it. Pretty straightforward. But the hard part is the conceptual part, is the superposition part. Okay, so what to do first? If we want to do the average, want to evaluate the average values. And emphasize many, many times. When you do average values, when you do probability calculation, the first thing you need to do is, what?
Square the.
Okay, you want to square it, but before you square the coefficient, you want to make sure the coefficient is what?
Normalized.
Normalized, exactly. So don't forget normalize the wavefunction first. Okay. The second one is, so here, within this expression here, Ci is Fourier coefficient, but I better to say this is normalized Fourier coefficient. I better to say that. And Ai is the eigenvalue of the corresponding operator. So if the A operator operated on psi 1, give you A1. Okay. All right, so give me one exercise. So give you some time and actually you can do it. Yeah, the evaluation may be a little bit math rigorous. So I only want you to show the way you do this one. But if you have time, you can actually evaluate it. I just feel a little bit time to math rigorous. Susan, nothing, Melissa.